Hello, and welcome to today's webinar with Emily Levesque. This is a particularly special webinar as we celebrate the first title from the new ebooks partnership with the American Astronomical Society. Astrophysics of Red Supergiants is the first book of its kind devoted to our current knowledge of red supergiant stars and provides a comprehensive overview of the fundamental physical properties of red supergiants, their evolution and their extragalactic and cosmological applications. Emily Levesque is an assistant professor at the Astronomy of the University of Washington in Seattle. Her research accolades include a 2017 Alfred P. Sloan Fellowship in Physics and the 2014 Annie Jump Cannon Research Prize from the AAS. During this webinar, we welcome your questions, so please use the Q&A facility to send them in at any time during the talk. Emily will then try to answer as many as she can at the end of the presentation, and we will respond to any unanswered questions once the webinar is over. So on that note, I shall hand you over to Emily.
All right. Hello, everybody, and thank you very much for joining us for this webinar. I'm very excited to be part of this new AAS and IOP book series and to talk to you a bit today about the book Astrophysics of Red Supergiants. I think a good way to start is to consider what red supergiants actually are. So red supergiants are the helium-fusing evolved descendants of moderately massive stars, so stars with initial masses of about 8 to 40 solar masses, and they're the stage that follows these stars being on the main sequence. So to briefly illustrate this, I've sketched an HR diagram at the bottom of the screen, and let's take this example of a 20 solar mass star. Right now it's sitting on the main sequence and fusing hydrogen in its core. It runs out of hydrogen in its convectively mixed core all at once, and then shifts to fusing hydrogen in a shell around a core that's now contracting to try and achieve the temperature and the density it needs to start fusing helium. Now, the rest of the star is still in radiative and hydrostatic equilibrium, so its luminosity is staying pretty much constant. And that contracting core combined with the fusing shell gives us our famed mirror effect, where if there's a fusion shell, the core and envelope behave opposite to one another. So the star's luminosity is staying constant, and its radius is increasing as the envelope expands. Since it's following this rough law, it means that the temperature of the star is going to plummet. So with the constant luminosity and a dropping temperature, we watch the star move horizontally across the top of the HR diagram. It briefly passes through the yellow supergiant phase during this time, but its whole crossing only takes about 10,000 to 100,000 years. So this is the explanation for that yellow gap that we see at the top of the HR diagram and the relative rarity of yellow supergiants. The star eventually winds up over here as a red supergiant. At this point, the core has started fusing helium. The star is almost the same luminosity, but it's now much cooler and it's much more physically large. So red supergiants are the very coldest and physically largest massive stars that we know about. An interesting thing to point out, too, now that we've traced this evolution, is that they are very distinct from red giants. These stars have higher initial masses, they have much shorter lifetimes, and you can see that they have very different evolutionary pathways. They don't do this dance up and down the red giant branch and then the asymptotic giant branch. So red giants and red supergiants have very unfortunately similar names, and sometimes very similar appearances, but they represent two really different types of stars and two very different evolutionary pathways. Red supergiants are also either the end phase or the intermediate phase in massive star evolution prior to core collapse. So some red supergiants will actually die in the red supergiant phase, while others will spend time there and then start shedding their outer layers and evolving back across the HR diagram. They evolve way back. They fly off somewhere to the left-hand side of your screen and become very hot Wolf-Rayet stars before dying. So the very cold temperatures of red supergiants that we see also give them really distinctive optical spectra. What I'm showing here is a model red supergiant spectrum produced by the Marks Stellar Atmosphere Group, and it's showing you the really distinctive characteristic of a cool supergiant spectrum. These spectra are dominated by big, broad absorption bands of titanium oxide molecules. These titanium oxide lines are the things that have long been used to measure spectral type in cool stars, And in red supergiants, we also see that they're very temperature sensitive. So if I animate this model and go from a 4,000 Kelvin red supergiant atmosphere down to a 3,400 Kelvin red supergiant atmosphere, you can see the titanium oxide bands appear and get much stronger as we go to low temperatures. If you watch the little slider bar, you'll also see the progression from early K-type to late M-type supergiants. So in the case of red supergiants, this is what gives us the very close correlation between their effective temperature and their spectral type. So I've gone through where red supergiants sit on the HR diagram and how their optical spectra look, but I feel like an important question to still address in this webinar is who actually cares about red supergiants? They're interesting, cold, massive stars, but why are they interesting? Who is really interested in these? So you are. Obviously, everybody who signed up for this webinar or who's watching it later cares a little bit, but you may still see connections on this list that you don't expect for either your own research interests or the research interests of your colleagues. So this slide is giving a sampling of the many fields that directly depend on our understanding of red supergiants. The book covers all of these in one form or another. I want to briefly highlight 3 of them here in a bit more detail. So we'll look at the relationship between red supergiants and gravitational waves, red supergiants and supernova progenitors, and red supergiants as they relate to strange and variable stars. So to start with gravitational waves, we all saw the amazing discovery this past August of a gravitational wave signature from 2 colliding neutron stars. This was especially exciting because it was the first case where we saw an electromagnetic counterpart associated with a gravitational wave event. So this event and many future ones, hopefully, are going to give us a completely new avenue for studying compact objects and where they come from. So something that's easy to forget in this excitement is that red supergiants are the pre-core collapse progenitors of at least some, if not most, neutron stars. So a system of colliding binary neutron stars has therefore almost certainly evolved from red supergiants in binary systems. So understanding binary interactions of red supergiants, understanding how these stars lose mass, understanding how this evolution affects their core collapse and their production of compact objects are all critical ingredients in studying things like binary neutron stars and gravitational waves. This is also a two-way street because understanding red supergiants will better help us interpret gravitational wave signals like this, and the gravitational waves in turn can help us constrain what we know about neutron stars and the stars that made them. So from this, it's also clear that red supergiants are interesting as supernova progenitors. They're both the direct progenitors and the intermediary progenitors of supernovae. So in some cases, we actually see very direct evidence of red supergiants exploding as supernovae. If we are lucky, we will sometimes capture pre-explosion imaging of a supernova progenitor, and one example of that is shown on the bottom left of the screen right now. This is pre-supernova imaging of the progenitor star of supernova 2008 BK. If we go from pre to post-supernova imaging, you can see very clearly that the star is now gone. So this sort of smoking gun image tells us that we can directly associate red supergiants with some supernovae. Very specifically, we've seen about a dozen red supergiants associated with type 2P supernovae. So to understand what a type 2P is, this subtype of supernova gets its name from the really distinctive shape of its light curve. You see a several dozen day flat plateau in the evolution of the supernova brightness shortly after the maximum. We are interpreting this as the interaction between the supernova shock wave and the very thick envelope of the red supergiant that's just died. So the shock wave ionizes hydrogen in the outer layers of the envelope. It basically gives us a temporary constant radius photosphere that makes the brightness appear sustained until temperature drops again and the hydrogen recombines. So with this collection of type 2P supernovae that we've detected, we can try to get some very direct information about supernova progenitors. If we're very lucky, as in the case of the 2008 BK progenitor, we can measure a color and a magnitude from the pre-explosion detection. We can use those to try and infer a temperature and a luminosity, and we can then try and estimate the initial mass of that progenitor based on what we know about red supergiant and pre-red supergiant evolution. The trouble here is that those inferences are really difficult. Getting a temperature and luminosity based on a color and a magnitude gives us some sizable error bars. And the masses that we infer can also be very degenerate depending on what we assume about the star's evolution. So the plot I've now put up on the lower right shows a handful of red supergiant progenitors that have been detected in this pre-explosion imaging, plotted on an HR diagram along with 3 different treatments of stellar evolution. So the solid lines are Geneva evolutionary tracks that are modeling non-rotating stars. The dashed lines are Geneva evolutionary tracks modeling rotating stars. And then those dotted lines are evolutionary tracks from the B-path binary evolution models. So you can see just from looking that we have data points with error bars that mean their initial masses could range from 12 to 20 solar masses, depending on what we assume about the red supergiant's pre-explosion evolution. So the more we know about these stars' evolution and their physical properties when they die, the better we can start to study these sorts of imaged progenitors. I also mentioned that red supergiants are sometimes an interim stage rather than a terminal stage for massive stars. So if you look at the rotating 20 solar mass model, and if you look at all of the binary models on this plot, the evolution predicts that the star is going to evolve back to become a Wolf-Rayet star before it dies. So because of this, we also really need to understand what happens to massive stars, their exteriors and their interiors, while they're red supergiants, and how this is going to impact what terminal phase they might eventually reach. And then finally, if you study time domain behavior of stars, or are on the lookout for any kind of unusual star, red supergiants are very important stars to know about. They're very strongly photometrically variable and spectroscopically variable in some cases. So the figure that I've put up at left is showing 4 different spectra taken of the same red supergiant. This is Harvard variable 11423 in the Small Magellanic Cloud. And if you look at the spectra from 2004, 2005, 2010, and 2013, there are very strong variations in the strength of those titanium oxide bands. This is in turn implying that the effective temperature of the star is either changing rapidly or appearing to change rapidly, and we're really still working on understanding why that might be. There are a bunch of different mechanisms that could contribute to variability in red supergiants, things like very large-scale convection on the surface of the star, radial pulsation behavior, sporadic mass loss, and what that mass loss does to the circumstellar dust around the star. There are cases where these stars can be hydrostatically unstable, and the presence of binary companions introducing things like eclipses or mass transfer or wind interactions can all affect the photometric and spectroscopic properties of a red supergiant. There's also the triple question mark bullet point, because we still have an incomplete understanding of all the different mechanisms that could contribute to variability in these stars. So all in all, red supergiants are clearly very important, but they're also complex. So working with them can be challenging if you don't have a detailed understanding of these stars and their quirks. And I want to go through one simple example of how you might want to use red supergiants and the different tricks that you might need to keep in mind. So the example I'm using is trying to identify red supergiants in other galaxies. This is one of the key appeals of stars like this. They're very luminous. They are great to observe in both the optical and the infrared, so they're excellent stars to observe even on an individual basis in galaxies well beyond our own. So if you want to identify a red supergiant sample in another galaxy, where do you start? You can think of it as a very simple way to start. You want to look for the red things. So what range of colors should we be looking for? We know that these colors correspond to the star's temperatures. And an interesting thing to keep in mind is that the temperatures of these stars actually shift as a function of metallicity. Red supergiants are lying on the rightmost edge of the HR diagram, and they're mostly lying along the Hayashi limit. This is the cold temperature limit for where a star can lie while still remaining in hydrostatic equilibrium. And that limit moves as a function of metallicity. The Hayashi limit itself comes from the opacity in the star's atmospheres. And the metallicity effect comes from the fact that we have more free electrons at higher metallicities. This gives us a higher abundance of ionized hydrogen, which is the main opacity source in a cold star's atmosphere. Opacity goes as temperature to the 9th for this opacity source. And what it means is that at higher metallicity, the ionized hydrogen opacity is higher. This gives us a shallower optical depth and a colder Hayashi limit. We're effectively not seeing quite as deep into the star. We see this both theoretically and observationally. So the plot on the right is comparing the Hayashi limit for Milky Way evolutionary tracks in black, LMC evolutionary tracks in red, and then SMC evolutionary tracks in blue. And you see the migration to warmer temperatures at lower metallicity. We also see this in data. The very narrow plot shown on the left is from Maria Drout's 2012 paper, which is plotting red supergiants on the HR diagram from different radii in M33. So as we move closer to the center of M33, where metallicity is higher, we see the red supergiants getting cooler and therefore redder. On the right, we see the same effect. We see a progression of average spectral subtype, which we know is determined by effective temperature, to earlier and warmer stars as we go from the solar metallicity of the Milky Way to the very low metallicity environment of the nearby galaxy WLM. So all of this means that red supergiant populations at low metallicity have a warmer average effective temperature and therefore a bluer average color. So if you're picking the same color range independent of host metallicity to identify a red supergiant population, you'll inevitably miss some stars. So okay, we've talked about what you need to consider finding red stars. You also want to make sure that you're finding supergiants. So what range of luminosities should we be looking for? So just like with our color or temperature cutoff, we want to pick a brightness cutoff. And if we look at a nice simple cartoon HR diagram, this should be easy. You just pick the luminosity that corresponds to 8 solar masses, draw a line, and we're done. We've selected very luminous supergiants. But the problem is that if we look more closely at this, we've definitely captured all the red supergiants, but some stars from the low mass giant branch are sneaking in. Contamination from these stars becomes a problem if we just draw the luminosity line directly at 8 solar masses. So this is the plot dropping a sample of presumed Milky Way red supergiants onto an HR diagram with, again, the Geneva non-rotating and rotating evolutionary tracks. We'd like to try and pick a minimum luminosity for the sample, but it's very hard. We could just take all of them, but then we get low mass contamination. We can try to be very strict and stay completely away from the evolution of any star below 8 solar masses, but that really hurts the completeness of our sample. You can see here that we could potentially miss those 2 9 solar mass red supergiants. And since, thanks to the IMF, most of the red supergiant population will be at the lower mass end, this can really hurt completeness if your cutoff is too strict. In practice, a common cutoff is about 10 to the 4 solar luminosities, but you'll notice we're still potentially neglecting some of the low mass red supergiants. So this is a fairly persistent problem with trying to really get a supergiant sample when we look at other galaxies. There's other parameters that also wind up impacting the luminosity range that we expect for red supergiants. Determining the distance to the population accurately winds up affecting how we use distance modulus to calculate the absolute magnitude. Knowing the metallicity of the host, again, starts to matter. There is an upper mass limit for red supergiants. We see this observationally as the Humphreys-Davidson limit. And this, in turn, is driven by the atmospheric Eddington limit. It's basically dictating that stars above a certain luminosity cannot cool off enough to become red supergiants while remaining stable. That atmospheric Eddington limit is metallicity dependent, which means that our maximum red supergiant mass and thus the maximum red supergiant luminosity should be different depending on metallicity as well. And finally, we know that calculating bolometric luminosity depends on the bolometric correction, which is also temperature sensitive, and temperature is in turn connected to metallicity. We know that these stars can be extremely dusty. The image on the right is the red supergiant VY Canis Majoris, which has an immense amount of circumstellar dust, and this can affect how we interpret its brightness and its luminosity. And finally, like I mentioned before, we know that red supergiants are very photometrically variable. So all of these complicate the range of luminosities you would want to pick when identifying extragalactic red supergiants. And then finally, once you've grabbed your sample, there are lots of contaminants that need to be considered. So foreground red dwarfs in our own Milky Way are really bright and really red, just like the background red supergiant. So we need to distinguish between them. One trick from a paper by Phil Massey in 1998, which is shown on the right here, plots the stars on a color-color diagram. The really different surface gravities between dwarfs and supergiants mean that we'll see really different line widths and thus very different amounts of line blanketing in the stars. This is especially true in the blue part of the spectrum, and that difference winds up separating dwarfs and supergiants on a V-R versus B-V plot. In this case, the dwarfs are shown in black, and the supergiants are shown in red, with supergiants that we then spectroscopically confirmed in blue. They follow a very different sequence on this plot. We can also use kinematics to distinguish between Milky Way and background galaxy members, but this depends on a good understanding of the background galaxy's kinematics itself. Another contaminant are foreground red giants. So giants are harder. We can again try to use kinematics, but there's limits to this. Something like a red giant in the halo can mess us up, although this is getting easier to distinguish all the time with missions like Gaia and other good proper motion studies. Surface gravity effects are proper motion and radial velocity. Surface gravity effects are more subtle now between giants and supergiants, so we don't see very drastic color separations. What we can do is use spectral lines like H alpha, which is the plot shown on the right, that are surface gravity sensitive to distinguish between lower gravity and higher gravity objects. And then finally, you can also get red background galaxies contaminating the sample. So sometimes these can be distinguished if you get very deep or very resolved imaging. But even that doesn't always work. A very dusty red supergiant and a fuzzy background galaxy could look similar in imaging. This can often only be resolved with spectroscopy. So a paper by one of my graduate students here at the University of Washington, Trevor Dorn-Wallenstein, was published just a couple of weeks ago in AppJ, and it discusses the surprise discovery of a background and periodic low luminosity AGN that by every standard imaging criteria looked like a red supergiant in M31. It took getting a spectrum, which you see on the bottom, to see the difference between a red apparent M31 member and a red AGN. So this has gone through just one example of why we need to understand red supergiants if we want to study them. So this then leads me into how I hope people will use astrophysics of red supergiants. I want to go through the chapters in the book and cover what the actual content is. So chapter 1 will give you an overview of red supergiants and their relevance. It's very similar to this presentation. Chapter 2 will cover the interiors of red supergiants, so their cores, their convective layers, and how these influence their evolution. Chapter 3 covers the standard physical properties of red supergiants, so their temperatures, luminosities, masses, radii, surface gravities, all the physical properties that we assemble to make a typical red supergiant. Chapter 4 deals with mass loss and dust production in these stars. We look at potential mechanisms for mass loss, the extreme cases of some very strongly mass losing or very dusty red supergiants, and their role in feedback. Chapter 5 specifically looks at binary red supergiants. We look at the observational sample, the role that red supergiants are expected to play in binary interaction, and extreme scenarios like compact object binaries, common envelope evolution, and merger products. Chapter 6 takes a more detailed drill down into what we just discussed, so how red supergiants in the Milky Way and in other galaxies are identified and then studied. In Chapter 7, we look at our current knowledge about photometric and spectroscopic variability in red supergiants. Chapter 8 specifically considers the role of these stars as they relate to supernovae, both as direct and intermediate progenitors. And then Chapter 9 looks at the future of red supergiant research, so how we'll be able to study and learn new things about these stars with facilities like James Webb, WFIRST, the extremely large telescopes, and LSST, and their place in gravitational wave astronomy. So the text in the book is very succinct. It's only about 100 pages, and it's been written at the advanced graduate student level. So the intent here is that people who are experts in massive stars and stellar evolution, along with people who work in different subfields but are just interested, can all use this book and take it in as a whole to get a complete primer on the current state of red supergiant astronomy. So my hope is that anybody that's interested in red supergiants can read this book, get that primer, and then keep it on hand to have it serve as a kind of standing reference for answering your questions about massive cool stars. So all of these are questions that I'll commonly get from people in related fields who are interested in learning more about red supergiants. All of these are addressed in the book. So this is how I hope that this book will be used by the larger community. On that note, I will wrap up the webinar portion, or the presentation portion of the webinar, and I'd be happy to answer any questions that you might have. Thank you very much.
Brilliant. Thank you, Emily. That was really interesting webinar and a great introduction to the book. We have received a few questions, so if you bear with me, let's have a look. First one we've got here. How common are red supergiants and how many are there in our own galaxy?
Oh, this is a good question. So even the question of how many red supergiants there are in our own galaxy is an interesting one, because we have an expectation of how many we should see as opposed to how many we actually observe. Our well-observed sample in the Milky Way is on the order of about a few hundred stars, and we expect that number to be much higher. Overall, there's interesting questions in the Milky Way for how to actually study these. The expectation is that there should be several thousand Milky Way red supergiants. We are likely missing some right now because of their location deep in the galactic plane or near the galactic center, although there are new clusters that have been discovered even in the past decade that are very red supergiant rich. In other galaxies, we can do a little bit better with getting a complete sample, but again, this is limited by things like possible contamination from super AGB stars and their confusion with very low mass red supergiants. So the overall scale we're working on is on the order of hundreds that we've looked at closely and studied well, but a big part of this is that there are many more that we can still look for and study.
Okay, thank you. Next question. What kind of activity do you see at the surface of a red supergiant?
So one thing that will dominate behavior at the surface of a red supergiant is convection. If you look at sort of a standard lecture on the sun, you see that we see little solar granules from the tops of convective layers in the sun, and those granules are tiny. In a red supergiant, the scale height is different, the convective scale is different, so the surface of a red supergiant is dominated by a handful of massive convective cells. So there's actually an animation that is included in the book that I have ready as a slide that I can show here. So this is an animation by Andrea Chiavassa, and it's showing the behavior that you'd expect to see at the surface of a red supergiant with these big convective cells. So this alone is giving us spectroscopic variability as we see the perceived temperature change. It's giving us photometric variability. And this doesn't even get into things like potential pulsational instabilities or other behavior.
Wow, okay, thank you. We're getting loads of questions coming in, which is great. So I will just pick the next one. So thanks, Emily. Is there a minimum H envelope required to produce a supernovae type 2P? Is that well related, brackets models, with a minimum initial mass of the progenitor?
It's a very good question, and something I was just talking about yesterday with a few people looking at this odd recent supernova, IPTF14 HLS. So we know that some amount of hydrogen envelope mass needs to be present in order to classify something as a type 2P. And that is more the purview of supernova models, determining exactly how much of a hydrogen envelope you'd need to have. The really interesting question here is that we want to try and understand how much of that hydrogen envelope can get lost. We've always seen type 2Ps associated with red supergiants, where we know that most of the envelope is still sticking around. We also know that these stars are strongly mass losing. So as they start to shed that envelope, it's unclear at what point a star can do that before it is no longer considered able to produce a type 2P. So this is an area where supernova models and stellar evolution models need to merge, and they unfortunately merge at this critical point of mass loss, where we still have a lot of unanswered questions.
Okay, thank you. Do all red supergiants die as supernovae?
So all red supergiants are massive stars, so at some point they are going to, we expect, die via core collapse, since these are moderately massive stars, about 8 to 40 solar masses. Some of them are going to die as type 2p supernovae. Others are going to evolve back into yellow supergiants or Wolf-Rayet stars and likely produce a different type of supernova. There's also the possibility that some of these stars will undergo core collapse directly into a black hole, and that this could lead to a vanishing star rather than the traditional rebound shock and supernova that we expect to see. There's actually one case so far observationally where we think that this has happened with a apparent red supergiant in the galaxy NGC 6946 that looks to have disappeared. So they're all going to undergo core collapse in some fashion, but there's a few different results for how that end product is going to look.
Okay, thank you. Next question we've got is that I've read that some red supergiants may have merged with neutron stars. Does your book talk about these, and could you tell us a little bit more about those?
Yes, so the book does talk about these, and the idea here is that you would have two massive stars in a binary, and one of the massive stars will undergo core collapse and form a neutron star. So you then wind up with a red supergiant and neutron star in a binary system. If that system undergoes a merger, this is a possible way to produce something called a Thorne-Zhitkov object. So in this case, you have a neutron star that is actually settled into and then replaced the core of the red supergiant. And this is predicted to be a stable model for how a star can exist. And what it would look like is a outwardly normal red supergiant that, upon close examination, has strange chemical abundances in its atmosphere from what that neutron star is doing to nucleosynthesis deep in the star. We actually think that we discovered the first strong candidate for a Thorne-Zhitkov object a few years ago in the Small Magellanic Cloud. There's still a lot of unanswered questions about these. We would obviously like to find more. It would be good to get a better understanding of the lifetimes of these objects, what their predicted final products are, and exactly how many red supergiants might actually be, Thorne-Zhitkov objects in disguise. So the book does go into these and what our current state of knowledge is, but it's also a very active and interesting area right now.
Okay, excellent. How many red supergiants are in binaries? Is that answerable?
That's a very good question. So there's a whole chapter in the book dedicated to red supergiants and their role in binaries. And I think there's two different ways to address the question. One is how many red supergiants we have observed in binaries. And the answer is surprisingly few, but there's a big caveat there. There are a handful of red supergiants. A couple of the famous ones are VV Cephei and Zeta Aurigae that have very clear observed B-star companions. These companions are actually orbiting in the winds of the star, so they're not examples of true mass transfer, but they're great tools for illuminating the chromospheres and winds of the star and studying them in detail. We actually have never observed a red supergiant with an obvious companion undergoing mass transfer. However, this could be due to observational limitations and not due to a total lack of such systems. Predicting how a system like that would look, where something like common envelope evolution comes in, determining how long or how strong the accretion lasts, is still a very active area of research. The traditional expectation is that red supergiants should be a really important ingredient in producing interacting binaries, that since they represent the physically largest phase of massive star evolution, they should be the key way of overflowing the Roche lobe and undergoing mass transfer. So it's an area that we very much need to understand more about, because these are such important ingredients in producing mass transfer binaries, and yet our observations and our picture of the binary fraction in red supergiants and how this mass transfer might look, that's all still very unclear.
Okay, thank you. Another question, how magnetically active do we expect red supergiants to be? How much could their internal dynamo contribute to observed variability in spectra and brightness?
Another really good question. So we do know of some red supergiants that have fairly substantial magnetic fields, and I'll clarify that these are surface magnetic fields. So Betelgeuse has an observed magnetic field of about 1 Gauss. We see Zeeman splitting, circular polarization from Zeeman splitting in the water masers surrounding the red supergiant ZX Sagittarii, and that suggests a surface magnetic field that could be as strong as 4 Gauss. So there's several other examples too that have 1 Gauss to several Gauss sized magnetic fields. The idea here is that this could be generated by a dynamo action that's in turn being driven by differential rotation between that expanding outer envelope and the contracting core. What this winds up doing to their observed variability is not something that's been modeled and would obviously have to be disentangled from all of the other behavior that's going on at the surface of a red supergiant.
Okay. Which methods are used to measure magnetic fields in red supergiants?
The method that I'm most familiar with is this idea, again, of looking at the circumstellar masers surrounding red supergiants and looking at circular polarization from Zeeman splitting. We can use a different technique with very nearby red supergiants, things like objects like Betelgeuse, but at greater distances, those circumstellar masers are actually a pretty valuable tool. And a surprising number of red supergiants have these. I think the estimate is that something like 15% of red supergiants show some amount of circumstellar maser emission, and you'll see silicon oxide masers, water masers, and OH masers. So this is a good tool to use for understanding circumstellar behavior, understanding mass loss, and in trying to probe magnetic fields. But a limit that comes up here, and something that gets repeated a lot in red supergiants with trying to very precisely measure properties, is that we simply don't have that many of them. And we certainly don't have that many of them nearby. So things like resolved interferometric imaging of red supergiant surfaces or similar is just limited by the small population that we have close by enough to observe like that. Okay,
thank you. Where's the next one I'm going to ask about? I think it's referring back to a slide that you showed earlier. Oh, I've lost the question, sorry, here we go. What is the duration of time of the red supergiants evolving in the HR diagram?
So it obviously depends on things like initial mass and things like metallicity, but the general idea is that the star is going to spend maybe 5 to 10 million years on the main sequence, and will then very quickly streak across the top of the HR diagram to settle as a red supergiant. We're now then talking again on the order of several million years that the star is actually a red supergiant, at which point it may undergo core collapse. It may evolve back across the HR diagram. To get very precise numbers, what you would want to look at are evolutionary models that select a specific mass, select a specific metallicity, and have careful treatments of things like mixing, which will affect how much fuel is available in the star's core, and how that mixing in turn is affected by things like rotation.
Okay, thank you. We've had somebody ask, how can we estimate the mass loss rate of red supergiants?
Good question. So there have been several different efforts to try and estimate this. When we talk about mass loss in red supergiants, it often gets very tangled up with dust production and circumstellar dust in red supergiants. Radiation pressure on dust grains is actually invoked as one potential means of driving mass loss in red supergiants. We get into a kind of funny chicken and egg problem where the dust would drive the mass loss, but in order to make the dust, you must have lost some mass. But these are generally based on observations on things like the mid-infrared emission from their circumstellar dust. There's a handful of red supergiants where their circumstellar gas can be directly detected, but again, we're limited by the sample where this is possible. So we'll generally be looking at mid-IR excess from circumstellar dust and then translating that into an empirical mass loss rate. Initially, this was agnostic of the mass loss phenomenon and just based on relating the estimated mass loss to other physical properties. So you'll see things like the Reimer's relation, where we just directly relate mass loss to luminosity, radius, and mass. And then more recently, there are calibrations from like Van Loon et al. 2005, or other recent calibrations that are looking at infrared spectra of red supergiants that are very dusty and trying to again connect dust excess to the star's physical properties.
Okay, thank you. I think we're getting close to time now, so we'll just have a couple more. We've got one. Can a red supergiant orbit a black hole, and what will happen to the orbit after the supernova as it becomes a neutron star?
Oh, that's a very good question. So the first part of it is certainly, yes, you can imagine a red supergiant orbiting a black hole. This gets into the interesting question of red supergiants as donor stars in X-ray binaries, and is a topic I'm actually very interested in current research. We have not identified a big population of X-ray binaries that have even post-main sequence donor stars. There are a few Wolf-Rayet black hole binaries. We've looked at potential LBV donors, but direct evidence of red supergiants with black hole companions and accretion from them producing X-rays is still pretty small. There are objects known as ultraluminous X-ray sources, ULXs, and some observations have suggested that they might have a red supergiant donor star with a black hole for a companion, but again, the sample is very small. As for what would happen after the red supergiant undergoes core collapse and becomes presumably a neutron star, it depends on the supernova itself, how asymmetric the collapse is, whether there's a supernova kick that unbinds it. If it does not, then we have this wonderful new example of a neutron star and black hole in a binary, which is interesting from a compact object perspective and from a gravitational wave perspective. So I know a lot of my answers seem to include things like, well, it depends, but that hopefully gives an idea of what the role that red supergiants would play in systems like that, and hopefully we get more observational evidence of things like this soon.
Brilliant. Thank you very much. I think just the last question we'll have time for today is red supergiants are studied as populations, but some of them as individuals if they are close enough. How are the studies feeding each other?
A lot of the work that I have done on red supergiants has been trying to hit a middle ground of that, of identifying a population of massive stars in another galaxy and then studying them individually. Every individual red supergiant that we study gives us another little puzzle piece of how their overall evolution is modeled. Taking individual stars lets us do things like plot them on an HR diagram, see how they compare to predictions of stellar evolution, and hopefully refine our understanding of things like their evolution, their mass loss, and everything else. Their populations are going to be especially interesting in the era of JWST or similar, where we start working with, say, very far away galaxies where we may not be able to resolve individual red supergiants, but we can resolve clusters. So we are already at that point in some cases in that the radius where we can do that will just get bigger when JWST or the ELTs or similar come online. And at that point, we can use observations of individual red supergiants as sort of ingredients or hints for how we would expect an entire population of them to behave.
Okay, brilliant. Thank you, Emily. That really is all we've got time for today. Thank you for your presentation, and thank you to everybody who's listening and who's taken part, submitted questions. Unfortunately, we didn't have time to answer all of them, so what we'll do is ask Emily to reply to those in writing, and we'll try and get those up on our website in the next few days. So please share the webinar. It will be available to listen to on demand in the next 24 hours. And the book, Astrophysics of Red Supergiants, will be available from iopscience.org/books before the end of the year. You just might need to check with your librarian for access. Thank you for listening, and goodbye.
Thank you all. Bye.